Hello, you will not believe how long it took me to get this camera working. OBS is just absolutely uh, pooping his pants, but I'm not going to go into too much detail. I just wanted to make a quick video, or a fairly quick video, unedited, because I don't have a good video editing software right now, uh, just to show off some cool thing I have learned while here in university. Well, technically, I kind of learned it. I also kind of taught myself, but just a cool property, so easier to show than explain. First of all, just gonna show my folder here. I have an assembly file and a C file. Let's have a look at min.c. So I am using Vim, by the way. I'm trying to learn how to use it, so I am a bit sloppy, but in time I'll improve. Here you can see I've got the C file over here. Very simple. You just got a number 10. You add 12. You print F, the number, and then it returns 0. And add 12, you can see here, down over. How do I do this? Over here, you can see that add 12 is just adding. Well, sorry, it's an external function because it is calling our assembly file. But you can also see that it takes a pointer as an argument because we're passing it by address. So what happens is that although you cannot tell here, because I have an implicit side effect, I'm adding 12 to the number within the function as like directly. So like I'm editing the reference of the variable. If you don't see, hopefully you know what that means. So to show you the actual ASM file, let's go pf and add 12. I don't know why it showed that. Okay, let's try that again. Pf. Okay, there it is. Okay, again, trying to adjust to this editor. So here we have the ASM file, which is very simple because it's not a standalone program. It just creates a linker file, which gives us our function add12. And very simply, I learned this assembly today, by the way, in a lecture. We have our text section. We have the global declaration of the name add12, which is what our C function imports. And then we have the actual code down here. So you can see so the first argument the function argument, which by the way was an int pointer, because this is a Windows 64-bit system, it takes a 64-bit pointer, so it goes to the RCX register. I'm not going to go too technical into detail, but basically it goes into the RCX detail. It fetches that value, moves it into the EAX register. So then we can then add 12 to the EAX register, or like at least do the add operation on it, and this adds 12. And if you remember in our C scripts, and by R I mean mine, I have the numbers as 10. So as you would expect, if I were to run add 12 on it, you would think this would become 22. And you'd be correct. It goes 10 plus 12, you get 22, and then it prints it. And in this final instruction here, it just moves the modified value back into the register, or at least like the address of it. Again, like this is all new to me, so I'm not entirely sure how it works, but something like that. Basically, like it modifies the value instead of returning the value, and then you have a return statement here, which may or may not be necessary. I assume it is, because I think it, right, because like it's an import, so it'd have to return back. I don't know. Tell me if you know in the comments below. So then if I again go back, back. Okay, so let's go ahead and compile these, because right now I literally have nothing. And this is where the cool stuff is, by the way. So I've not memorized these commands, so yes, I am using Gemini just to remember. I'm using NASAM, so NASM, however you meant to pronounce that, to compile this. So it's NASM F, I guess, for file. I should probably learn these formally. That's my system. And then my file's called add12 .asm-o, which is the name, and we'll just do add12. Actually, you know what? I'll do add, because little spoiler alert for what's going to come later. Okay, no, that's for the actual thing there. Let's go down. Okay, so that's for a standalone program. This is what I want to do. NASM F24 maths ops. Okay, yeah, ASM. Yeah, so just .o. O I assume is like an object file of some kind. Turns out that, well, I'll show this later, but turns out that C and ASM both compile to the same O file. Not entirely sure what that means, but I hope to find out. And then let's compile our C file. So just C for something, I don't know, main.c-o main.o. Okay, no errors there. And then let's have a look at the binary representation here before I run anything. So we got the two object files, or I assume they're called that, COF file, whatever. You can see that they do have the same format, which you can tell here, first of all, by the same fact that it's using the same template, for those who are familiar with U10 editor. But if you're not, then just, you can also see from the file signature over here, if you open the file header, we can see that the thing at the top is a specific header for a machine thing, apparently. Since it says AMD64, my AMD64, I don't know. I thought it was on Intel, but anyway, that is the file there. And you can see here we have our function name at 12, and then on the main, we have main. I'm not too worried about main. I actually do want to focus on this. But before I get too ahead of myself, let's go ahead and compile. So to compile while linking, you do GCC, GCC by the way, C compiler, main.o, and our add.o, so both of those. Then you just do, okay, pretty simple, -o main.exe. Okay, so now we've created a main.exe, and then if I run it, 22, right? Because 10 plus 12 is 22. And now a little cool thing. I mean, it's not that mind-blowing, but obviously when you compile the program, right, it will convert your code into machine instructions. So you would expect there to be something that says add 12 here. And, you know, as me who is learning assembly for the first time, I'm very curious to see how this assembly gets converted to machine code. So let's have a look here. There's only one section header, and it is text. We can see it here. So let's go down to text. And if you expand this, we can see we have, if I'm not mistaken, I think the name, long name. Well, no, this isn't right. Where was it? Was it here? Sorry, I went to the wrong one. It's our section. Symbols, just symbols. The section is the actual thing. Here we have our data, and this data is the machine instructions, or so I believe, because you can look here. We can see we have these instructions down here. I can also see them in my inspector, which my face is covering, but whatever. You can see them here, and you can see here. Well, actually, I'll open this in Vim as well. So again, and Vim as 12.asm. Okay, you can see here that we have our instructions there. So what's first? Move the RCX address register into EAX, something like that. And sure enough, we have move EAX, dword pointer, RCX address. And dword is a 32-bit pointer, I think. I don't know. And then you have add EAX. So this is our add thing over here. 0xc is just hexadecimal way of writing a number. So 0x is the hexadecimal label that tells us this is a hex number, and then C is 12 because 1, 2, 3, 4, 5, 6, 7, 8, 9, A is 10, B is 11, C is 12. And then you have the move dword pointer RCX as the final instruction. Well, and then return as the final instruction, but this is the final non-return instruction. So this is cool, and obviously, you know, I'm thinking, because I've kind of learned about like opcodes and all this stuff, and I'm like, okay, if this is what is being converted to in machine code, and by the way, I'm surprised that it's literally line for line the exact same. Can I modify this? And the answer is yes. So two ways we can do this. Well, at least that I've only tried one, so I'll try the other one in this video as well. But for the first one that I have tried, you can see here that when I click on this in the very handy template table, it highlights these 3 bytes. And I can only assume that these first 2 is for the add and EAX commands. So maybe C0 represents EAX. I'm not too sure. Maybe 8.3 represents add, or maybe there's some complex combining here, considering the thing is technically, you know, if I switch to binary view, like this is the actual representation. So you have like these bits here would just be the instruction add EX, add EAX with the second operand being the number, and this here is just 12. And funnily enough, it literally says 0, 1, 2 here. Why is that? I'm guessing this is might be decimal. I don't know. Anyway, so if I go back to hex view, here, so this is 0 C. Let's change this, right? Let's say I want to go to 69. Hilarious number, right? Now, if you recall, in my main, the initial number was 10. So what do we need to add to 10 to get 69? Well, 69 minus 10 is 59. So let's change this 12 to 59. Now, I could literally write this out as hexadecimal, or you can just use the inspector, which I'm covering, but it is down here. And we can just go ahead and modify this to 59. And because 59 is well within the range of a 8-bit signed integer, for positive numbers, then that should be okay. Because I have actually tried this with values greater than 128, I think is the limit, and it goes negative. So for whatever reason, there's something here that says it's unsigned. But anyway, let's go ahead and save that, and now let's recompile our exe. Okay, I can quit Vim, and then we should get 69. So let's go ahead and link them again, get our main.exe, and let's run main 69. Perfect. So just like that, without even modifying our source code, I have changed the machine code directly to change the output of our program. Now, obviously, this is a very simple example. What are the, I'll get into the implications of this later on. But just one more thing I want to do. We have created an exe, right? And I would expect that I would also be able to change the machine code in the exe, because ultimately an exe, again, like it just contains machine code, and somehow it gets, I haven't studied exes or apps in general for that matter, but I know that there's machine code in there for sure. So let's go ahead and try and find that with 0 editor. Here's our main.exe. Let's open it up. Now, this file is a lot longer, and I mean a lot longer than everything else. I reckon it's probably because you can see here it's including like a bunch of build things from MinGW, which is my GCC compiler. So like a bunch of C stuff here, I guess. There might be a bunch of like Windows things, boilerplate, whatever. And this file is 64, well, about around 64 megabytes, I guess. So it's a lot. And I've seen a video, by the way, of how you can like reduce the size of it. It's really cool. Of exe, sorry, which is really cool. But this is what we have. And obviously trying to find our instructions here would be a nightmare. So what I'm going to do is I'm going to just simply, again, take this command. I'm going to copy the hex bits here. So copy as hex text, or you can do Control-Shift-C. And then let's just go do a search. So Control-F. My hex bytes are here. I'm going to Control-V. And then, again, make sure this says hex bytes, because I'm searching for hex bytes. Press Enter. And there is, in this case, only one occurrence, which is great, because that means there's no confusion. And here I have what I assume is the command. And I can also look around it with this, like, other stuff around. That should be the same. Yes. So this string of bytes here is the exact same as string of bytes here. And once again, I'm surprised that this just got put exactly as I said. No optimizations. I mean, it's just adding 12, but I digress. It was just completely left intact, this string of bytes, which is obviously really good for testing purposes. Obviously, you can disable all optimization, but I digress. It's cool. So, to test this, and I have not tested this yet, let's go ahead and change this. So 3b was our value, 59. Let's say you want to do a different number. Let's do 26, because it's the year 2026. So I'm going to change this to 16, because 10 plus 16 is 26. And 16 is an easy number in hex. It'll just be 0, 1, because it's base 16. Look at that. So let's go make sure we're in overwrite mode. Just do 0, 1. Let's go ahead and save. I'm a fool. It's 1, 0, because it's 1 times 16. And then now, let's go back to our terminal and just run main. And hopefully, 26. Bazinga. So there you go. Cool. Machine code, ASM, awesome. Now, I mean, yeah. Why is this important, right? So, For those who don't know, I'm a big modding fan. And by fan, I mean I also mod myself. I make mods. I've made mods before for a game, well, for many games, but especially JoJo's Bizarre Adventure All-Star Battle R. And one of the cool things about that game is that we have a JoJo API. And what JoJo API does is it hooks into the game and it loads, well, I mean, like it, yeah, loads its own menus and like injects DLL stuff. I'm explaining this horribly, but essentially it's a mod loader. So it can hijack the game's code, load its own custom stuff, API, and then that will make modding easier. And I know other things do this. Like I'm sure, well, I'm not sure, but I assume stuff like SM API for Stardew Valley might do this as well, and whatever other APIs exist. I actually don't really know them all. But it's cool because the idea here is that if the thing just compiles to machine code, what you can do is just hijack where the jump command, for those who don't know, assembly uses jump commands to go to different machine, like areas of machine code, let's say. So like let's say it goes well, very simple example. Let's say my game calls a start function, right? So in machine code, let's say jump to the start label or jump to whatever position, whatever address has my code for the start process. By process, I mean just a list of instructions, like literally just a list of instructions byte by byte. So if you just hijack that and say, okay, instead of jumping to this location, jump to my own custom location, well, then you can hijack it and you can do whatever code you want. You know, you can run whatever code you want. And although this is one way you can get your computer hacked, it is also a way that you can mod a game. So, you know, what I've done in this video is very, very simple, you know, like literally day one assembly stuff, because I'm a day oneer myself. But just it's kind of cool to think about the implications, and hopefully those of you who are not so familiar with assembly, if you watch this far into the video, hopefully you find that interesting and inspires you to do a bit of playing around yourself. Thanks for watching. I just realized I can't really. I'm not editing this, so thanks for watching.